And yeah, I just wanted to show the famous images once, because in the original paper, this is what the authors used to describe the scale dot product attention, and you see Q and K go in. You see it on the board on the right-hand side. With the matrix multiplication, we have the scaling with the dimensionality. This masking has to do with if you want to, in a decoder architecture, predict next tokens. Then there is the soft argmax, and there is another matrix multiplication with V, and that's it. Yeah, and so this is the sketch that they gave, and here I put it in formula. And when I first gave this course 2 years ago, I really took quite a bit of time to reverse engineer, not reverse engineer, I mean, anyway, to understand in detail what are the formula behind all this. And this has become a lot simpler in the meantime, because by now there are really nice textbooks. And in particular, the third one I did not know until last week at all. So this one here, I like it. This one you can find a legal free PDF copy. This is the one I just learned about. I also like it. You can get not a PDF, but on the website of the book, there is a sort of browser version of it, which you can read. And this is actually a very good match with the contents of the entire course. And I was a bit shocked. I looked at the convolutional neural network chapter, and it's, I mean, basically the same stuff that I told you last week, same selection of topics. So, without talking about it beforehand. And this is a famous guy. His first textbook was on neural networks before they became fashionable. So it was in the fashionable again in the late 90s. Then he wrote this very nice, but also very Bayesian book in which there's no principal component analysis because that's not sufficiently Bayesian. That's the book on pattern recognition and machine learning, which I already referenced at some other point. And now he brings out this book, and I'm very happy to see that there's even PCA in there, even though it's not Bayesian. And yeah, Chris Bishop is a research director at Microsoft and heads the AI for Science initiative there, and thinks about machine learning as a fifth paradigm of science. I quoted him at the beginning of the term. And this one is also a really nice book, and as far as I know, not legally available online. It also has the advantage of being relatively thin. So this is, I don't know, maybe 250 or 300 pages. This one is already 600. So I very much like this one also. And had these books been around 2 years ago, that would have saved me a lot of time. All right. Good. So we have discussed this, and now we will discuss that. Yeah, multi-head attention by adding plenty more indices to our board. It's not so bad. We just add indices. So we have added a superscript L to say that we have many layers, and it turns out to be a good idea to let each sample ask not just one, but different questions. so as to have multiple attention heads in parallel. So, and now we fill in the blanks here. In multi-head attention, so schematically what we have is that, and I'm now drawing this from top to bottom as is usual, we have our input XL and then we have our our new features XL plus 1. We've seen that there is a skip link here, right there. And here previously we had this attention block. And rather than a single attention block, we can now have multiple heads in parallel. So in this case, I'm plotting 3 heads, and that would be 1 layer. And then this, of course, goes into the next layer, and we replicate. And you do this a few times, and you end up with billions and billions of parameters. Yeah, so these some of these matrices here can be really large. And the interesting discussion from the break was about, you know, where is the meaning stored in such a large language model? And here we talked about the coordinates of single words, but the meaning of the sentence as a whole, it is reflected in the activations of your large language model. And if we now try and interpret such a large language model, because hundreds of billions of activations, that's a complex thing to try and understand. So something that you can do is you can force the information to flow through a bottleneck layer. And bottleneck is a bit misleading because normally in an autoencoder, our latent space dimension is smaller than the ambient dimension. But here it's the other way around. You start with an input, which is, let's say 4096 dimensional, and then you put it through a latent space which has perhaps 50,000 dimensions, and then it goes back. But what's special about this latent space is that in here you enforce sparsity using, for example, the L1 regularization that we have discussed at length. So if this has a dimension of 50,000, we have 50,000 perceptrons in here, and our sparsity regularizer encourages the network to only use 1 or 2 or 3 of these to propagate information. And then we can let this loose on a large corpus of text. Yeah, so we can let it loose on the internet and then say or ask which sentences led to the activation of a particular neuron. And then as a human, we can look at those sentences and see that they were discussing democracy, and the perceptron next to it was responsible for baseball, and so on. Yeah, so there's no ordering, but it turns out that each of these represents some concept, and some are pretty concrete, like there might be a perceptron for Abraham Lincoln, and some are very abstract, like justice or so. So these are sparse autoencoders that can help the interpretation in large language models. And okay, the good thing is they become more interpretable. The bad thing is if you do this kind of brain surgery, the model becomes a bit more dumb. Yeah? So you can, you will of course need to train or fine tune it, but the model is not quite as good as if you don't do this. And in January, let's see, 6th is a Monday. On January 7th, we will have a special lecture by two experts. One is Lennart Bürger, who is still a master student, but has published one of the best papers worldwide on detecting lies in large language models. He's still writing his thesis in our lab. And the other one is Erik Jenner, who is working on his PhD in Berkeley in the field of AI safety. And they will tell you, more about this and how to detect lies and how the next generation LLMs can work around those detectors. So January 7th should be, I'm much looking forward, should be really cool. All right. So meaning is stored in the activations. Okay, now coming back to these multiple heads here, so we can now say we let each word ask not just one kind of question, but we let each word ask several kinds of questions. Yeah? So I'm adding a new index H here for the head. So the first head in this layer L gets one kind of weight matrix, and the second head gets a weight matrix of its own, and so on. And so I get not one set of queries, but multiple set of queries. And so let's say I have capital H heads here. And similarly for the other equations here. Good thing I didn't wipe the board. And all right, and now comes a small departure here, namely if we do this naively, well, this will inflate the number of parameters by capital H. And it turns out that you get a better deal by making each of these heads a bit smaller, and rather, if you still have more compute, invest into more layers. So in particular, it is okay if this matrix here is not squared anymore. So I'm now changing the dimension here of this one to become P. I'm writing here at for attention times P. And this is something smaller than the ambient dimension. In fact, it is quite typical to say that if I'm using the number of heads, so H times P attention, I get P back. Yeah? So in other words, I have used the same number of parameters as in ordinary attention. I've just now distributed those parameters across more heads. And so I obtain now slimmer matrices Q, K, and V. And so wherever I previously here wrote P, I now write P attention. And you see that I still obtain something n by n, yeah? So nothing has changed here. But this was P attention, and that one was P attention. And now I can combine these outputs from the individual heads by just concatenating. Yeah, so I'm now writing that ZL is I'm writing this as a matrix here. And the first subpart of the matrix would be ZL comma 1. And then I have other parts, and down here I have ZL comma capital H. And this is now my new matrix ZL, which I am again using down here. So overall, nothing has changed in the dimensions of the overall output. So this was P attention times n. This thing is again P times n. And so my output also is P times n. All right, and this now was multi-head attention. Any questions about that? Yeah. A multi-graph neural network, my understanding would be that you have hyper edges, so edges connecting more than two nodes. It's not really the same, because here each item can attend to all others. So this is always a completely connected graph. So the graph is always complete. It's really more that we have several of these layers here in parallel. Yeah? No, each of the heads uses the complete graph. Yeah, it's not the same as multigraphs here, or multi-graph network. Thank you. Any other questions? Yes.
Computationally easiest to run things in parallel, or is there some different results?
Yeah, so the question is, why reduce the number of parameters here? Yes, we want to limit the number of parameters, both to keep training feasible and to make it less expensive at test time. And so it's always, you have this architectural space, like how many layers do I use, and how many heads do I use, and how many parameters do I give to each head. And this is, of course, arbitrary. Yeah, I could also say that, this is 2 times P or whatever. It has been engineered extensively, and it's found that seems to be a reasonable choice, but there's no, deep reason for having that equation here. No. The question was, do we use multi-head attention to make it faster? No, it is to make it produce better answers ultimately. So I always said that one word attends to others, and a word could ask different questions to its neighbors. Yeah, so each one sample question could be that a word asks, am I a verb corresponding to such and such a noun? Or it could be, am I a verb whose tense is defined by such and such? Or it can be more semantic things. Yeah, am I a verb that describes more abstract things? Am I a verb that describes an activity or not? So it's just, you can invent all kinds of questions that one item could ask to the others. And here, all of these questions are asked in parallel and are used to update then the features. So so these things have billions and billions of parameters, and training them, that's I found that a surprising idea, that Microsoft and Google, that they reopen or build new nuclear power plants just to get enough electricity to train these things. So that's lots of parameters, and that's lots of compute. And this has also been very intimidating originally for the academic community, because most universities don't happen to have a nuclear power plant or 100,000 GPUs lying around. But people came up with smart workarounds, and there is, for example, something called LoRa, or low rank approximation. And the idea of LoRa is that okay, we take a model that was, for example, trained by Meta, the Facebook owner. Their model was originally leaked, and then once it was leaked, they decided, okay, we'll now just release our models. And there, you can use such a pre-trained model, and then not try and find the whole matrix W, but rather find just a low rank change to it. So we could say that we take a WQ tilde, and this is the original WQ, plus this is a P by P matrix, a low rank approximation which just consists, for example, of a rank 1 correction. Yeah? So this here is P times 1, and this is 1 times P. And this is not very many parameters. Yeah? And this you can do actually on a single GPU. And that in turn led to a bit of panic, for the companies with 100,000 GPUs. And there was a famous blog post. There was some discussion about, is it real or fake? It is called "We Have No Moat." A moat is, if you build a castle, it's the thing you build around to protect it. Yeah? Der Wassergraben. And this blog post panicked that, look, we need a nuclear power plant and 100,000 GPUs to train our models. And then somebody with a single GPU can come and fine-tune our models, to become even better, or to become better at specific tasks. And there was a bit of panic, like, we might not have the advance that we thought we would. Yeah, so very, very interesting. All right, but back to your question, I said that it's just found that it works better to have multiple heads rather than just one fat head. And what do I mean when I say better? At the end of last time, we were discussing how do you train models with many parameters? Where do you get the training label from? And so if, for example, I wanted to train a transformer from scratch, let's say on tweets, and I take as classification problem, is this tweet, is it hate speech or not? Or is it fake, is it fake news or is it real news? Then you need somebody to sit down and label this as, hate, no hate, and so on. And there's only so many labels that you can pay. However, there is basically, not unlimited, but there's plenty of text on the internet in all languages. And so a very important task, training task, has been to just predict the next word. And even if you take, let's say, you know, a blog post, or even if you take a fake news post, you know, the contents might be rubbish, but you know, you know, looking through a looking glass at the language itself might be okay. Yeah, so let's say you take a bad novel, and there are you know, plenty of free bad novels out there on the internet, and you take a good novel. You know, once your model becomes really intelligent, it might learn more from the good novel. You know, it might learn more from Tolstoy than from some, you know, really poorly written adventure thing. However, when it just comes to learning the mechanics of the language, the bad novel is actually good enough. So you can use all this rubbish text to bring your model to a level where it has understood language in an abstract sense, and also in a specific sense, because there's English and French and German and so on. And then once you have that, you can then start fine-tuning your model. And Letizia will tell you more about that next week, where you know, tell the model to you know, not indulge in conspiracy theories, and you know, not be mean, and you know, you teach it to do all kinds of things. But this is comparably, it's more expensive because you need human labelers, but it's a much simpler task than making the model learn language and learn logic and all that in the first place. So predicting the next word is a really, really important task. And now here I made the point that attention is a permutation equivariant. So it's a bag of words model so far. So he swung. So if we have these words, he swung the club, you know, if we want to represent it as a graph, it would be a complete graph. Everything is connected to everything. Or I can just say it's a collection of words. Yeah, so I'm trying here to show, okay, that's my artistic rendering of a bag. And if I manage, I put a, right, okay, this is just a bag of words. In such a bag of words, it's a start, but you can easily construct examples of sentences where the ordering of the words really matters. Yeah, I mean, by changing the order of the words, the meaning can change completely. So the ordering of the words matters, and this is why a positional encoding is needed. And the first attempts for positional encoding went like so. So if we have here our matrix P by N, the first attempts at positional encoding were to just add a few extra dimensions and to say, okay, maybe I'm adding lots of extra dimensions, and to say for each word, or to code in these vectors for each word, where was your position in the text. And now you can invent many positional encodings. You could, for example, say, okay, let's just use an indicator vector. The problem is with my indicator vector, you know, I've now reached the end, and now I don't know what to do here. I can either repeat the same indicator vectors, or maybe I now need to add, you know, a second, you know, a second entry, and then here maybe I can add, you know, a third entry. So I'm inventing a not very good positional encoding here. One that turned out to be better for a variety of reasons was to just use sigmoids. So to code here from left to right harmonic oscillations of different frequencies, because that allows you to more easily measure distances. But this now came at the price of doubling the dimensionality of our input. But you know, hey, these are engineers, so they decided rather than concatenate, you know, let's just add the positional encoding. So here are my harmonic oscillations. Here are my original features. You know, let's just add them to obtain a new set of features, which I'm going to call whatever, x tilde. And then I'm putting that into my transformer. And well, you know, in this trade-off of how many parameters do I invest where, it turns out that this works good enough. And then as always, you know, the engineers do something, and then after the fact, we try and figure out why does this work in the first place. And here the argument is that, all right, this is a high dimensional vector, that's a high dimensional vector. If you take any two high dimensional vectors, there is a good chance that they are orthogonal. So, you know, hand-wavingly, this is sort of orthogonal information anyways, and then the transformer can figure this out. And, you know, if you have 100,000 GPUs and if you have a nuclear power station to train this for ages and ages, then it turns out that the transformer can figure this out. Okay. So we have looked today at attention and multi-head attention, the building block of transformers, and more on that and how they in turn are used in more flexible language models. We will have on Tuesday next week. Have a good time.